Hi there, this is Jacob Nash, and in this video we'll be starting a new course, and it's going to be physics. So I've already done some physics videos before, but it was mostly for AP Physics 1. I did that about like 3 years ago, but now we're going to be looking at more college level physics. I guess technically AP is supposed to be, but this is going to be taught from like a college lecture standpoint. And in this video, we're just going to be talking about vector basics, velocity, and acceleration. So, welcome to these videos. If you haven't seen my channel before, I've been making videos for about 5, 6 years now, and uh, I try to simplify things in the best way that I can because I always say that in most cases, it's not impossible for you to understand something. And, typically what I do is math is most commonly the videos that I make, which this is really science and math. But um, the thing I want to say is that these videos really can't substitute your need to complete practice problems. So, um, especially with more advanced types of classes like this, you're definitely going to want to complete a lot of practice problems so that you'll just get used to all the different types of things you might see. Because one of the things that's gonna make this class a little bit challenging is that there's not really always a specific way to solve every problem that works for every problem. So, there's a lot of things that you did in high school where it's like, I just know this is exactly how it's going to be. You do this every time for this type of problem. Well, this time it's not going to be like that. It's going to be very situational, and you're really going to have to think um, deeply about how you might solve that problem. But I will try my best to help with that. We're not really going to get into that in this video, though. This is just the first one. Um, so questions and feedback is definitely welcome in the comments below. Um, I don't look at that super often, but I definitely will check every now and then if you have any questions. Um, Also, I have still the AP Physics videos up. If you happen to take AP Physics, even if you didn't, you might have never taken any physics class, but that might be useful to you as well because those are going to go in a little bit more depth than what I'm going to have here, just for time purposes, because we have a lot of content to cover. And these videos would be like 90 minutes long. So this isn't really meant to also be just like a substitute for like lectures that you might have either. It's supposed to just be simplified. So, anyways, why can physics be hard? I kind of already just said this, but it's almost all word problems that you're going to be doing. So you'll just be given some information and then it's like solve for this. So that's not all that you can see, but that's definitely going to be a good amount of what you'll see. And it's not going to just always be so cut and dry of what method you would always have to use. So, but we'll think of some strategies later on. So we're going to just start talking about one-dimensional motion. Obviously, in the real world, um, we have three-dimensional motion. If you just kind of think about like if you just hold out your hand, you can move your hand to the left or right, up or down, forward and back. Those are three different directions. But right now, we're really just going to talk about one and uh, a direction just on one plane, basically, if you want to think about it like that. So we're going to talk about three different things here. and all of them are related to each other. So if you've taken calculus before, if you haven't, that's fine too. But if you have, you might have learned about derivatives and integrals. And that's can apply here. And if you don't know what that is, that's completely fine. But all three of these values, if you want to say, or um, calculations are related to each other in the sense that if you draw a graph of these in relation to time, then the slope or area under the curve is what relates it to it. So if that doesn't make sense, you'll see what I mean later. But we're going to start out with the first one of the three, which is going to be displacement. Displacement and distance are not the same thing, though they're similar, but it's kind of one of those things like, um, you know, a square is a rectangle, but a rectangle isn't a square. It's like one of those things where it can be the same thing or it just might not be. Basically, displacement's a more specific version of distance, if you want to say. And it's what we're going to be looking at. And the reason why is that it accounts for direction. We care about if you're going in a positive or negative direction in physics. So distance doesn't help us that much because, like, if I stand and I walk forward 1 meter and then backward 1 meter, the distance is going to be the same, right? It's just going to be 1 meter, um, each direction. But uh, it's if you are going in what's perceived as the negative direction, which is usually backward, down, or left, then that's going to have a negative attached to it, which is not something we'd see for distance. So this is a good example too. If I run in a circle, let's say that there's like a circular, you know, track in a park and I run around it, um, the distance is going to be, the circumference of that circle, obviously. So let's just say it was a half of a mile or whatever. That's the distance that I ran. But my displacement's going to be zero if I start and end at the same place. Because it's saying, well, I don't care that you went that far. You're at the same place, so displacement zero. So that's the difference between them. But th like I said, displacement is what we're going to look at, and we can use delta x to define that. Delta, if in case you don't know, that triangle, that means change in. So that's going to be the final distance, or sorry, final position minus the initial position. So it's always for delta, it's always going to be final minus initial. See this right here. Um, so, we use those subscripts, F and I, to know what final and initial are. Now, I want to say if you took AP Physics, different symbols might have been used. So you might just need to erase that out of your memory and just use what I'm using, or even if your professor prefers something else, just do whatever symbols are required for your situation. So we're going to talk about position now, which is just basically what leads us to be able to calculate displacement. But this is where an object is, obviously. And we can use a coordinate system to define this. For now, just x and y. Um, Hopefully you're familiar with the coordinate system, probably been using that. Uh, Position is something that we consider a vector. And a vector, I put this here because if you know Despicable Me, you probably know it has direction and magnitude. So those are the two components of a vector. So basically what we're saying is position can tell us those two things. And keep in mind that up and right are perceived as positive, whereas down and left are perceived as negative. But if we're talking about a vector representation of displacement, instead of that delta x that we saw before, let's use delta r with that line over it, which indicates vector. And right here, it's the exact same thing as this formula I showed you right here. We still see that F and I, but we're instead just using that R with a line to show vector. Um, so we can add and subtract vectors, and this will make more sense later on, but because we're going to look at more examples in the next video, but we're just going to briefly talk about how you would add and subtract vectors. And this might seem strange a little bit, but let's just say that we have two vectors, A and B. So you might have a visual representation of what these would look like on a coordinate system. And let's say A looks like that and B looks like that. Well, the B is always going to have its tail on the tip of A. So the tail meaning the start of it. See that? So B has its tail on the tip of A. That's the second thing you do. And then if you want to add them together, you put the tail of A to the tip of B. And yes, it's not like, oh, just make it a triangle, like it matters which direction it's going. So that's why you have to make sure that it's uh here to here, not the other way around. So that's how you would add vectors. Those are the steps for that you're going to want to remember. Now, subtracting, it's a little bit funky. So still same thing. You would draw A, but B, whatever the vector of that is, you're going to make it negative. And if something is negative in this situation, it's going to be flipped. So if you remember on here, the blue one, it went down like that. Well, now it's going to go like that. So it flipped around because it's negative B. Because we're really doing the same thing. We're still adding the vectors, but for it to really end up subtracting, you have to add by a negative b, which sounds kind of strange, but if you do a plus negative b, it's the same thing as a minus b. So we're doing the same thing as we just did, but the only difference is that we just flip b. And so same thing, put the tail of A to the tip of B, and it's like that. So it's a little bit different. But that's what you would do for subtracting them. So now, that was the first of the three things I said we were going to talk about. That was displacement. Now we can talk about velocity. Well, just like how we had distance and displacement, there's also speed and velocity. Speed is not going to tell us direction. I can say I went 2 miles per hour or 2 meters per second, I should really say, because we usually use meters in this class to just let you know, or in this class, I don't really know how I'm saying that, but anyways, uh, so I could say I went 2 meters per second, but like in what direction? Speed wouldn't tell me that. Velocity does. And here's where I was talking about the derivatives and integrals. If you look at a graph of displacement versus time, we might have it like this, um, where that's x for displacement and t for time, and it's like something like that. All right, we're seeing that the distance is increasing, but it's flattening out. So it's not increasing at a constant rate as time increases. Well, the slope of this thing is also what you would call the derivative. And that slope is the velocity, which just means like what the slope is the change in rise over run, as you know. And so we're saying, how does displacement change? It's not constant. If it was constant, it'd be like that. That's a slope of one. Um, or if it just didn't move at all, it'd just be that flat. And that would just be slope zero. But in this case, the slope is changing, which means that velocity is changing as well with time. So it's not a constant velocity. This would be constant velocity. This would be zero velocity. This is changing velocity. So that's how you can think about it like that. Now, once again, we're going to use that r vector in this case. Um, but this v velocity vector, it's also a vector because it has direction and magnitude as well. That's the whole freaking point of why we use it versus speed. And the unit is meters per second. Um, like I said, we're going to use meters typically in here. And so distance or displacement will use meters as the unit. But why would it be meters per second? Well, just what this formula is. The unit for this R is meters. The unit for the T is seconds. So it's meters divided by seconds, meters per second. So that's why it's like that. Um, it's important that if the displacement is zero, so would the average velocity be. Because if this numerator is zero, that would make the whole thing zero. That's algebraically, I guess, how you could think about it. Um, and once again, if that's what this situation would be, if there's no displacement, so would the velocity be zero. So now let's move on to the next slide. We're going to talk about linear acceleration. And why do I say linear? Because there's also rotational that we'll talk about. But linear um, acceleration is the third thing that we're talking about. So now we're going one step further. Now, like I said, we had that displacement versus time graph. And the slope of that thing was going to be how we could get the velocity versus time. And the slope of this thing is how you could get the acceleration versus time. So that's called, we're taking a derivative to get to the next thing, further and further. And you could do it one more too, and uh, talk about that later, but not right now. So that means that this is going to be uh, velocity, change in velocity over change in time. Um, and since the change in velocity is change in displacement over change in time. That would, of course, mean that the acceleration is change in displacement over time, all over time, which is why that it's meters per second squared as the unit. So same thing for these deltas, always do the final minus the initial. So what was the ending velocity minus the starting? It's almost like the rise over run, and why is because I just said the slope of this thing is going to be this thing, and that's what this looks like, right? This looks like the slope formula that we know. So you can think about it in that way too. Um, Now you got to be careful about that because since velocity is a vector, we can have a change in magnitude, which means the speed can change. And if the speed changes, then if the velocity is not constant, then that means we do have acceleration present. If the velocity is constant, then acceleration is not present. So that's how you can look at it. So that's all the content that I'm going to talk about right now. We're going to get into more depth and some examples in the next video. But now I want to end this video with just talking about a few sneaky tricks. So the first one is um, for formula switching. So you might like let's just think about that formula that we just had for the acceleration. So if you want to reorganize this formula in terms of velocity or time, sometimes that can be a little bit tricky for some people. And a trick that I like to use is just to write a random division problem that you know. So let's just say 8 equals 16 divided by 2. That's just random, but that is true. And that looks like that formula just with numbers. So let's say, all right, if we wanted to solve for time, that's 2. So what is 2 relating to these numbers? 2 equals 16 divided by 8. So that means time is going to be change in velocity divided by change in acceleration. So you can do things like that. That's kind of, that at least works for me. Now, another thing that you're going to have to do is change units. As I mentioned, we use meters, but let's say they give you something stupid like yards. Well, in that case, like let's say, all right, we want to convert it to inches first. You use your conversion rates so you know how many inches is 1 yard, and the units there would cancel out because there's the numerator and denominator right there. And then if you then wanted to, you knew how many inches is in a meter, you set it up like that so those units cancel out. And if you don't get what that means, just wait till there's an example and you'll see. But that's a quick way to change from units if you're far off from what you need. Because yards, if you need meters, that's kind of annoying that you have to do more than one step, but it makes it a little easier if you do it like that. Then the next thing that I want to say is KFES. If you watched my videos ever in 2022, this was the acronym that I used for how you can solve word problems. And it works for almost all types of word problems that you see. That doesn't mean that it's going to be easy every time to do this. Um, but just having this in the back of your head will take away some stress of you solving a word problem if you are the t type of person that doesn't like it. So K stands for write down what you know. So always just write down what they tell you. All right, they told me the velocity. They told me this, that. Write that stuff down and just be like V equals and just write down what you know. Then write down what you need to find. Because nothing's worse than if you accidentally solved for the wrong thing. So it's simple thing, but just make sure that you can do it in a bullet format so that that whole long paragraph doesn't just kind of stress you out. So you can just write down what do you need to find. Then you're going to write E, which means equations. So you're going to write all the equations that are applicable, and we're going to learn a lot more equations in this class. So write down all the equations that are applicable for the K and F. So any equations that contain those variables from what you know and need to find. And then using those equations and the numbers, then solve that problem. So, like I said, it's not using this method doesn't mean it's going to make every problem easy, but it's going to help because especially with this E, this is going to be like a bridge because you might think, well, are there any equations that even have those variables from what you need to know or what you know and what you need to find? If there's not, you might actually have to do some conversions or use other equations to get to a different variable, and you'll see what I mean. Um, but that's going to be it for this video. I apologize if it was seemed a little bit like hard for me to gather my thoughts. It is kind of late when I'm making this right now, 12:14 a.m. So anyways, uh, looking forward to the next videos and thank you for watching.